네. 네. 어, 네. 네, 약간 CR에 나오는 게 좀 너무 복잡해 보이긴 한데. I assume that you all read this abstract. So, like, I think this abstract is really some like classical and typical abstract. It has really clear gaps and tests. So, designing chemical reaction networks that implement desired dynamical properties really challenging, and it remains largely manual. Yes. So, do you have any like different thought or like impression for this abstract? Well, it's on archive. Let's move on. So, like to model how this like different chemical reactions evolve in the time, we typically use chemical reaction networks. So, or if we imagine a really simple network, then we can think of this kind of simple first reaction and the best reaction. And we also have even more complex networks like this and this, which involves like two or three species, chemical species. And from this chemical reaction networks, and all the chemical reaction network shows different dynamical properties. So dynamical properties means that they how their like amount of species evolve is different from each network. So it can be like really simple increasing with saturation, or it can be show some writing stability, or it can also show the oscillation. The one like really well-known area and the well like researched area is if we have one chemical reaction network, then we can predict their dynamical properties. So one simple method would be the using differential equations. So if we have this kind of network, and if we want to know how the concentration of the X1 will evolve from this network, then we can write this kind of differential equations. So this differential equations means that this X1, concentration of X1 will increase with this burst rate of the X1, and the concentration of X1 will decrease with this KD, the degradation rate of the X1. So if we know the initial concentration of this X1, then we're having a set of these ordinary differential equations. So if we simulate this ODE, then we can check how this X1 concentration will be evolve over time. So, some our kind of limitation of this ODE-based method is that if we have multiple cells, and if they share this same chemical reaction network, then from this ODE simulation, what we know is regardless of the different cell, they are showing the identical this beautiful curve of exon concentration. But in reality, it does not happen because they are different cells, so they are in the different environment. So because of the noise from the environment, they shows really different trajectory of the exon. So to take account this effect, we have another simulation algorithm for simulating the checking the dynamical property of this CRN, and we call it the Gillespie algorithm. So today's target focus of today's talk is not a Gillespie algorithm, so I will really briefly explain the Gillespie algorithm. But if you want to know more about this Gillespie algorithm, please tell me after the journal. So what this Gillespie algorithm do is that basically it will some simulating some sequence of the reactions, chemical reactions. So and what it do is it samples when the next event will occur. So as you can see in this example, it samples the waiting time, the time interval between this event and the next event. And what Gillespie algorithm do is it also determines which event is this. So in this network, we have two possible reactions. One is birth and one is death. So Gillespie algorithm determines the timing of each reaction and the type of the reaction. And from this some sequence of the reactions, what we can do is we can know the trajectory of the X1 for one cell. Then if we repeat this for the multiple cells, then we can simulate the different trajectory of X1 in the different environment. So to summarize, from this chemical reaction network, CRN, by using ODE or Gillespie, we can easily know the dynamical properties. Yes, but the opposite direction, once we have desired dynamical properties, it is hard to get chemical reaction networks which have that properties. Like for example, the best example case is my paper, my research activity. So in short, what this paper discovered is that using this, you can see this green chemical reaction structure, we can have a really nice dynamical property, which means that after the perturbation in the system, we have same consistent mean and consistent noise level for the network. And to check if this CRN shows this dynamical property, we can use Gillespie algorithm. And if we want to really get a minimal result, minimal investigation, then it just takes 10 minutes. But to discover this network from this desired property, I spent 6 months to discover this just 4 reactions. So this shows 10 minutes and 6 months. This shows how this discovering CRN is really challenging.
Within 6 months, it took more.
Like just for the idea 6 months and like more like investigation and simulation took like
Couple of years.
2 years. So why this is challenging is that let's think really naive approach for discovering the CRN. Then what we can do is we first set the really broad library of the reactions, which has like tons of possible chemical reactions. And we just pick some of them. And we complete the CRN structure. And we simulate it and check if this is a match with what we want. And we repeat this process until we get our desired property. Then, but it took really much of time because let's assume that we have like 100 reaction in library. Then the possible some combination of the chemical reaction structure is e to the 100. Then if we assume that we need like 1 second for simulating one combination, I mean a second for one CRN, then we took 2 to the 100 seconds, which is 10 to the 22 years. But the age of the universe is 10 to the 10 years. So you have to watch a Big Bang for like 10 to the 10 times to finishing this simulation. So in this, it's impossible. So basically, we have to do like conceptually, we have to do similar thing. We have to pick one CRN and we have to check the dynamical property and we have to do it again and again. But can we do it like more intelligent way? This is the like main question of the authors for this paper. So if I repeat, to discover the CRN, we will do similar thing. We first generate the CRN and we check if it is a desired property what we want, and we update this like intelligent agent, and we generate the CRN again and repeat this process. And the key is that how can we do this upper part more like intelligent way. So in more detail. So this agent will starting from the like initial chemical reaction structure, it will append the reactions like this. This agent will append the reaction sequentially, and it will do a similar thing several times. And what we will do is from this terminal CRN, we will simulate them, and we will check if they have a desired property. And from this first result of this first generation of the CRN, we will update this agent and do same thing. So in this process, the key step will be how this agent choose this next reaction to append, and how this agent should be updated. So I will first explain this first one, how the agent choose the next reaction. So if agent choosing a next reaction means that this agent will have to choose the next reaction to be appended from some reaction library, and it has to determine its parameter value. So for example, if this is the current CRN, and we want to append one reaction to this CRN, then it means that from this reaction library, which consists of 5 reactions, we want to choose one reaction. For example, like ID3, and we have to determine the parameter values, like for example, zeta3. So to do that, what we need is we need the ID of the reaction and the parameter values of the reaction. So agent means that agent will sample that ID and parameter from this probability distribution. And probability, this conditional probability distribution can be like decomposed in these 2 parts. And so the agent means that agent is these distributions. So yes, so for example, you can imagine this kind of thing. Given this CRN, what we want is we want to have this kind of values, probability values, and for the this parameter, we want to know their like distribution. And yes, so to do this, we are adopting the neural network, so simple MLP. So this MLP, what this MLP do is its input is the CRN, and its output is this project values. I mean the probability values. And for this distribution, its input is ID. I mean, from this distribution, we can sample one ID. Then we have an ID. Then from this ID and current CRN, it goes into the NLP, and it samples the mean and variance of this parameter distribution. So from this parameter, this distribution based on the neural network, we can sample the ID and CRN. It means that we can sample the next reaction. So we repeat this procedure for multiple times. Yes. So this procedure is the first procedure in the whole procedure in the previous slide.
이를 한번 더 설명해 좀 주세요. 쉽지 않은 거죠.
So so our goal is we have to choose the next reaction. So if you see this one, then we appended this red reaction. Then what we want to do is how should we determine which reactions to append from this reaction library? And to do that, we need 2 things. One is the which reaction, like this ID, I mean this ID, and which parameter. So to sample these 2 things, ID and parameter, we need a probability distribution of the ID and zeta. And to form this probability distribution of the ID and zeta, we will use the neural network. So if I repeat, So we need a parameter distribution of the ID and zeta, which depends on the current CRN. So, yes, to form this distribution, we will use the neural network. And the first step for doing this is we will first decompose this distribution in two parts. One is for the ID and one is for the zeta. Because the reason we doing this is because this zeta can be the dimension of the zeta can be defined by the ID. Because as you can see, this ID one has one parameter, but this ID for the first reaction has two parameters. So we decompose this ID and zeta. And to form this two distribution, so for example, this distribution will be something like this. Given the CRN, we have the probability distribution, the discrete probability distribution for the ID. And so it means that, in other words, it is the function of the CRN which gives us the probability of this ID. So we will, but we don't know that function. So we will replace that function with a NLP, neural network. Similarly, we need to form the distribution of the parameter. In this case, this distribution is the function of the reaction ID and the current CRN. So it is the function of ID and CRN, but we don't know this function, so we again replace this function with a neural network.
I'm like understand what does the conditional probability means. The ID zeta conditions on CRN. Is it kind of like the probability that kind of certain ID plus CRN satisfy some kind of conditions, or
it is something like if you look at this, it means that currently we have this CRN, and for the next reaction, we will pick reaction 5. Then what is the probability distribution of this zeta 5?
where does it come from? So because I'm thinking that the parameters we are free to set. 그러니까 제 파라미터라는 뭔가 그냥 정한다라고 생각이 드는데 파라미터를 샘플하는 건지 아니면 뭐 새로운 리액션 템플릿 아이디를 붙이는 건데 또 그냥 선택해서 붙이는 게 아니라 왜 그게 샘플 될 수 있는 건지. 예를 들어 자연에 막 존재하는 모든 CRN을 가져와서 프로베비티 디스트리를 만든다면은 그렇게는 이해할 수 있는데 그런 상황 아닐 것 같아요.
네, 그래서 이거의 목적은 그거예요. CRN을 일단 그러니까 제가 맨 처음에 나이브한 어프로치라고 설명을 한 거는 CRN 그냥 싹 다 모은 다음에 다 시뮬레이션에서 체크를 하는 거예요. 근데 여기에서도 CRN을 일정 수준 이제 샘플링을 할 건데, 이제 그 샘플링을 하기 위해서 이 디스트리뷰션이 필요한 거고, 이제 이 디스트리뷰션을 이제 계속 업데이트를 할 건데, 이 디스트리뷰션의 형태가 어떤 식으로 되냐면은 약간 이런 식으로 된다.
그럼 예를 들어서
네.
예를 들어 뭐 오실레이션의 성질을 원한다라면
네.
그게 나올 수 있도록 샘플링을 하는 건가요?
그게 나올 수 있도록 이제 이 뉴럴 네트워크가 계속 업데이트가 되는 거예요.
네.
This model, we need to determine the number of reactants, right? Reactants. Because here, I think we need to build that reaction template. This is based on like fixing a figure looks like we already fixed the number of reactants is 3.
Yes. Yes.
So it be predetermined.
Yes. Right.
And also, I'm more of, so maybe you will explain later, but I'm very curious about the form of NLP because this, how we can get a CRN as an input. So how we can transform CRN as a numerical value.
So actually, it's in appendix, but like so basically we will convert the CRN to the vector.
Vector, right?
And so we have yes. So yes, first we convert the CRN to this kind of matrix. So for each reaction, we can check if this reaction exists in this CRN or not. We encode that as a 1 and 0. And for each reaction, we can read the parameter values. So we have parameter column, and this input is just for indicating we have external input in the reaction rate or not. So if we concatenate this vectors in one vectors, then we can make the vector of CRN, and we use this CRN as input for the ML.
So then, depending on the number of agent and also the target some dynamics, we need to train each NLP for each problem.
Right.
Okay, it's very inefficient.
Yeah. Okay, so if we change our desired dynamical property, we have to do all things. Okay. Very quick further session.
약간 그 변수 선택이랑 약간 비슷한 느낌이 보이긴 하거든요. 원래 변수 다 넣어보는 거가 안 돼서 포워드로 다시 넣어보는.
네네. 근데 그거에다 그냥 네, 맞죠.
거기다가 약간 reinforcement만
네, 맞죠.
그거 기반에 variable selection 느낌이죠.
네네.
땅에 들어가면
네.
네트워크가 얼마나 저 네트워크가 얼마나 높은 확률을 가지고 있냐 파라미터가 얼마나 선택 확률이 높다 이런 거를 하는 거예요. 그러니까 다음 이런 네트워크에 뭔가 리액션 점점 더 추가해가면서 내가 원하는 밸런스를 가지고 다음에 뭘 넣을 건지 결정을 넣을 건지
네.
결정하는 거고 네, 조정하도록.
네네. So like in one whole sentence, we will choose the reaction, and this reaction will be chosen by this MLP, which has an input as an whose input is the CRN. And this MLP will be updating and or other words trained and to sample the CRN, which has a dynamical property, what we want. So, and to do that, what we can, yes, we have to set some loss function for this, for match this dynamical properties. So for example, if we want like consistent output or from the CRN, and what we the simulation from this sample CRN is this blue curve, then we set the loss function like this. So we integral the difference between this x trajectory and this consistent output C. So it means that if we minimize this loss, this x will be similar with this C. So we have a consistent output. And this is the example case of if we want consistent output, but this loss should be changed if we want like different dynamics. I will show the different example in the later part. And what we will do is we will minimize the this loss. In other words, we optimize this reward, which is just negative value of this loss. And then, because we have n multiple CRNs, we have n different values of the reward. And if we sort it, then we may draw this kind of graph. Then what we will do is we will pick top like k reward values, and we set the baseline value for this top k. Then we calculate this excess value. And what we will do is we will optimize this excess value, exceeded amount of the reward, so that we can match more to this desired property. Yes, so like in short, we want them to match with this consistent output by using this reward.
We can add reactions to generate the desired dynamics. So this MLP function determines when to end this adding.
When to end.
Finish this adding.
So number of this step, number of this step is predetermined by the user.
This was fixed.
But it doesn't mean that it fixed the reaction to be appended, because in the reaction library we have no reaction. Just
no
reaction.
I see.
So
okay.
Yes, we are just setting the maximal number of the reaction, but not the actual number of the appended reactions. Yes. The one problem of using just this prior is that, as you can see in this curve, you can think this is some step or like updating step of this MLP, and this y-axis is the loss. So yes, and as you can see in this region, even though you like keep update the MLP, this loss does not decrease. It means that like keep updating this MLP does not improve the performance. So in this case, we can just think that we are just sampling the really just similar CRNs. So we should seek really new CRN. So it means that we have to simulate the new we have to sample new ID and zeta. So it means that we have to agents should make this probability distribution of ID zeta more like broad. So in more like quantitative way, we can force this by using entropy of the probability distribution. So if we maximize this entropy of the probability distribution, you can imagine if we increasing the entropy of the probability distribution, you can have more like broader distribution, so that you can have more like chance of having a really new sample. So this entropy looks complicated, but it is just sum of the entropy of choosing a reaction and entropy of choosing a parameter. So by increasing this value, we can choose a new reaction and new parameter. So more precisely, because we have really many CRNs sampled here, so we sum the entropy values for this some chain, and we take an average for this n different chains. So we use this value as a reward, and we add it with rows what we defined in the previous slide. And in this graph, this black line is the loss from our loss formed from our desired dynamical properties, and this red one is the loss from this entropy. And as you can see, if this dynamic loss does not decrease anymore, then we increase this reward. We increase this entropy so that we can seek the some more new reaction.
This is basically when we sample n networks, we want very diverse type of network. So to be ensure the diversity of
Right. So like if we summarize this two like reward function, and from this reward function, we are updating the agent so that this reward function can be increased. I mean, we are updating this p to increase this to reward function. And with this updated agent, we will sample the next generation of the multiple CRNs. And one concern is that because if we sample the second generation, we forgot all this first generation and we start from the really initial CRN here. So there is some possibility that some outperforming CRNs in the first generation is better than the second generation. So in this case, rather than using this red second generation, we better choose this some performing CRNs in the first generation. So to check if this some good CRNs in the first generation is better than the second generation, we will add additional reward term. So first we check the among this second generation, we calculate the maximum reward. And for the first generation, we are choosing a top like K amount of the good CRNs, and we will save them, like holography. Then what we will do is if we add this reward term, it means that if this CRN in the Hall of Fame is better, is worse, then it means that this R star is better. R star is higher than this RS, the reward of this Hall of Fame. So because of this term, this becomes negative. So this whole term becomes 0. So this plus sign means that if it is 0, if it is negative, then it output the 0. And if it is positive, it just gives its value. In the other case, if the member of the Hall of Fame is better than this maximum reward, then increasing this reward function means that you want to increase this value, log of this probability. And this probability means that probability of sampling this member of the Hall of Fame. So it means that if the member of the Hall of Fame is better than second generation, we will increase the probability of choosing them. So using this 3 different reward term, we will keep update the agent. And by simulating the multiple generation of the theorem, we can get a multiple servants that satisfy the dynamical property what we want. Okay.
그게 first하고 second generation 다른 이유가
first generation이 한번 나오고, 그 first generation의 결과를 통해서 그 MLP가 업데이트된.
second에서 업데이트가 된다.
네, 맞아요.
그러니까 저 first는 그냥 생성만 하는 거예요.
first, 그러니까 generation이 계속 이어지는 건데,
네.
first에서 이게 하나가 만들어지면 걔를 통해서 이제 에이전트, 그러니까 MLP가 업데이트가 되고, 그 업데이트 된 걸로 세컨드 제너레이션을 다시 만들고, 그 세컨드 제너레이션의 결과로 MLP를 또 업데이트하고, 그 다음에 세 번째 제너레이션 만들고, 그거를 계속 반복하는 거예요. Yeah, so like even though I just wrote like first and second generation, we will repeat this for multiple generation. So from the result of the first generation, we will update the agent, and with that updated agent, we generate the second generation. And from the results of the second generation, we update the agent, and we are sampling the third generation, and we are repeating that for multiple generation. So we hope that in the like really like or 20th generation or something like that, we have really good theorems which satisfies the dynamical property what we want. So using this framework, they named this framework as a GenAI-Net. And the authors investigated if they can really generate the theorem of what we want. So in this case, the objective of sampling the theorem was this. So in this theorem, we have one input, and from this input signal, this amount of the X3 will be changed. And what we want is, depending on this input, we want this output to change following this curve, which is the hill function, this hill function. So by like keep simulating this, then AI get before that to form the loss function for this objective. What they did is, yes, for the different inputs, as what I noted as like U1, U2, and U3, we can compare the steady state of the X3 and our desired value, which is the hill function of the input. So we can form our loss function like this. We are integrating the difference between the simulated output and the desired like, steady state value, which is the function of the input. So using this loss function, GenAI-Net generated 40 theorems, and as an example, so we can observe these 3 like representative theorems, and they look really complex. But if we simulate them, if we simulate their like this input and output like, response curve, then you can observe this one. So this colored curve is the input and output response from this 3 theorem. And you can also see this really thin gray curve. Then gray curve is another like 37 theorems generated by the GenAI. And as you can see, all the curves is matched with this black dotted line, dashed line, which is our like target value. So it shows that all 40 theorems what generated from the GenAI-Net has the desired dynamical property, which is this one. And
when we think about objective, for each rate you want, we get some amount of x3 at some time, right? Even some time.
It precisely it is steady state.
Steady state.
And we can also use this GenAI-Net for the oscillation. So in this case, we have to set the loss function really carefully because we have to quantify this oscillation. So first to do that, we first change the center of this simulated output of the theorem. And from this zero-centered output, we are calculating the autocorrelation function for that zero-centered output. Then, if we calculate this autocorrelation function, then we have this kind of curve depending on this time lag. So autocorrelation function is the correlation between the original curve and the some delayed curve. So if this autocorrelation is high in certain value of this time lag, for example, if the original curve and if the correlation of original curve and the 24-hour delayed curve is high, it means that it has the periodicity of the 24 hours. So high value of autocorrelation means that it has periodicity of this tau value, this time lag value. So what we want to do is we want to maximize this autocorrelation value so that we can ensure that it really has a periodicity. And so this term is this. So by minimizing this term, we are maximizing this autocorrelation value. And for this one, it is just matching a center of the oscillation to our desired oscillation, like this. So by using this loss function, then GenAI-Net simulated sample 100 theorems. And again, if we plot all the 100 theorem, then you can observe this curve. So in this case, as you can see from this colored curve and even for the gray curve, you can see that they all have the oscillations. So it means that this GenAI-Net successfully sample the theorem which shows the oscillation. And additionally, what we can do is which reaction did GenAI-Net choose to make an oscillation. So we can summarize the result of the GenAI-Net with this heat map, not a heat map, this map. So in this map, the one dot represents one theorem. More precisely, one dot represents the one reaction in one theorem. So for example, if you see this theorem, it has this kind of autocatalytic reaction. Then we are adding the dot in here, which represent the reaction from x2 to x2 plus x2. And by repeating this for the 100 theorems, all the reaction in 100 theorems, we have this map, which has really many dots. And as you can see, there is some block which has really many dots. It means that GenAI-Net choose this reaction to make oscillation, which possibly means that this certain reaction is important for making oscillation. So one representative example would be this one, which is x1 plus x3 go to nothing. And in more biological sense, it can be seen as a titration or sequestration. And this titration and sequestration is the key mechanism of the circadian clock, our circadian clock. And other representative example is that x2 plus x3 to x3 plus x3, and the x1 plus x3 to x3 plus x3. And if we carefully look at this reaction, it can be seen as some kind of negative feedback loop, because if the x2 increase, then x3 increase. Then reaction of this x3, this reaction increase, it means that x2 disappears more quickly. So it decreases the x2. So it can be seen as some negative feedback loop. And again, this negative feedback loop is the key mechanism of our circadian clock. So by using this math, not only just generating the CRN, we can do more kind of scientific research to discover which reaction is important for, which reaction or mechanism is important for making a certain dynamical property. And as a last example, yes, so in here, the dynamical property, what we want is after some perturbation or disturbance in the systems, we have to maintain the mean, stable mean, even after the disturbance. And we want to keep the noise of the output, which is graphically some width of these multiple trajectories of the output. So to quantify these two things, what we can do is we can calculate the mean and CV. So CV is the standard deviation over mean. So we can first calculate the mean and CV. And to achieve this first objective, we can form this loss function as the integral of the difference between the simulated mean and our desired value for the target mean level. And to minimize this noise, if we just integral the CV, then minimizing this means that minimizing the this standard deviation, so that we can keep small noise. So using this, yes, and we are calculating this loss function for the different condition. Different condition means the different type of the disturbances in the system. Then using this loss function, we can generate multiple theorems. And yes, as you can see in this graph, all the theorems, so yes, all the theorems achieve the desired mean level even after the perturbation. So yes, so perturbation point is around this point. And if we compare with the CV of the original network means that CV of just this network, X1 degradation of X1, then it is smaller than the original noise level. It means that we achieved a small level of the noise from this CRM. So yes. So again, we sample the 40 different CRNs, which shows there's consistent mean level and small noise. And we again this similarity, we spread we summarize all the reactions in these 40 different CRNs, and we can check which reaction is important to make this property, which is like stable making and small noise. And if I pick two reactions from this, then it is like X1 plus X1 to X1 and X1 to C3. And this dimerization of the X1 and making one species is really similar with what I discovered in my paper. It dimerizes first and makes one species. So to discover these reactions, I spent like 6 months, but this GenAI-Net only took 20 hours to find this reaction. So it is 180 times better than it. So in summary, yes, in summary, this GenAI-Net, once we define the dynamic core property what we want, then this GenAI-Net trains or update the agents which sample the CRN. And by repeating this updating procedure over and over, then we can finally have a good CRNs which have the property what we want. That's it.